Hello everyone. So my name is Haoran, and today I talk about my PhD project called Xu-Deegen-LLVM-Based Compiler for dynamic languages. Wait, is the speaker working? Oh yeah. Okay, so today we'll be talking about dynamic languages, and I guess I don't need to explain what is dynamic language. I'm sure everyone has heard of Python or things like those. And thanks to dynamic typing, it's quite easy to program in a dynamic language. But due to the high level of dynamism on a simple VM implementation, the execution performance is poor. And it's really hard to build a good VM. So let's take a look at the state-of-the-art VMs. So the thing is that in order to execute fast, we of course need a JIT. And for a JIT, the compilation happens at runtime. So the thing is that the compilation time is part of the execution time. So we cannot simply only have an optimizing compiler that spends a lot of time in compilation. The thing is that we have to spend some of the time in compilation and also some of the time in execution. So we have so the end result is that we actually need two JITs. One is called a baseline JIT that compiles fast, and the other is an optimizing JIT that spends a lot of time in compilation and generates higher quality code. And the end result of this game is that we need at least 3 tiers. The code starts executing in an interpreter, and eventually hot code gets tied up to the baseline JIT tier, and eventually even hotter code gets further tied to the optimizing JIT tier. And this architecture is followed in the state-of-the-art VMs in general, like JavaScript Core and V8 and the SpiderMonkey. So as you can see, while an architecture like this gives you a high-performance VM, it takes a lot of engineering cost to implement this. And the LLVM as a compiler infrastructure, it seems quite natural to use LLVM to like reduce the high engineering cost. And of course, I'm not the only one to have this idea. In the past, there are already attempts to use LLVM for Python, for Ruby and Lua and a lot of other things. But as you can see, despite the many attempts, they are not quite successful. So why? So to summarize, the main problem is that LLVM compilation is very slow. So LLVM is a highly optimized compiler, and the code generated by LLVM is really good, but the compilation is totally not good. But however, for a JIT, it's important to have to compile fast, since as I said earlier, the compilation happens at execution time. So the compilation time is a part of the total execution time. And the second issue of LLVM is that it has no direct support for the important domain-specific optimizations. For example, in order to optimize things like table access, object access, we have to have inline caching, and the efficient implementation of inline caching is self-modifying code, and the LLVM is not really designed to do that. And the LLVM is also designed for static languages, and it has no support for dynamic type optimizations. And also, the thing is that we have to have more than one VM tiers, so we have to think about how to tire up and how to OSR exit. And LLVM has no support for that. So how do we solve these issues? The core idea is that we are not using LLVM as a compiler. Instead, we use LLVM as a compiler. So the thing is that we take in the semantic of the language implemented in CPP as a single source of truth. And statically, we automatically generate this JIT. So this part, so the thing is that statically, at build time, we use LLVM to automatically transform the execution semantic of the language to the architecture similar to the state-of-the-art VMs. And now we have done the optimized interpreter and the baseline JIT part. And I'm in the progress of implementing the optimizing JIT part. So let's take a look at some numbers. So in order to actually test this idea in the real world, we have implemented a standard compliant VM for Lua 5.1. And the execution engine is automatically generated by Xu-Deegen, which includes an optimized interpreter, a JIT compiler, and the tiring up logic right now. And importantly, we have inline caching optimization. So to summarize the performance, for the interpreter-only performance, it turns out that we are about 31% faster than the highly optimized LuaJIT interpreter, and 179% faster than the official POC Lua implementation. And for the JIT tier, the compilation cost is negligible, and the generated code is about 34% slower than the LuaJIT's optimizing JIT, and 360% faster than the POC Lua. The thing is that here we are comparing the optimizing JIT performance against the baseline JIT performance, so it's quite natural that we are slower. However, as once we don't have completed the optimizing JIT part, hopefully we can eventually have higher peak performance as well. And now let's take a look at how all of these things work. So as we explained before, the input is a semantic execution semantic of the language bytecodes. And in this example, we have an add bytecode. And as you would expect, it takes two operands, LHS and RHS. And here we just check if LHS and RHS are both double. And if not, we simply throw out an arrow saying that cannot add. Otherwise, we cast LHS and RHS to double, do the add, and say that the outcome of, what's going on? What's going on? What? And say that the outcome of this add is just the LHS casted to double and RHS casted to double. And here the thing is that the throw arrow and the return are APIs in Xu-Deegen, and the throw arrow, as you would expect, throws an exception, and the return is an API that says the outcome of this add is this value, and the is, as, and the create APIs are defined by the user. So the thing is that Xu-Deegen can understand the type hierarchy of the language, and it can do optimizations. And yeah, that's it. And now let's take a look at a slightly more complex. Wait, why is battery? Now let's take a look at a slightly more complex example. And here, at the time we check LHS and RHS type, if it's not a double. Wait, what? Wait, I've connected the battery. Okay, here, at the time we check LHS and RHS type. If it's not a double, we will call beta method similar to an overloaded operator to execute this add. And here the interesting thing is that is this make call API. So it allows us to call a guest language function, and it never returns. And at the time the call ends, the control is transformed to the continuation functor. And here the continuation functor just says that the end outcome of this add is the first value returned by the core. And the continuation passing style is needed for dual stack for coroutine semantics, and also it allows us to know that a core always happens at a tail position, which is important for optimizations as well. And the execution semantic is not the only thing in the language. So we also need to know things like an add has 2 operands, and every operand is either a constant or a temporary value in the stack frame. And that's this operand thing says. And we also need to know that an add always generates a value. And the implementation is the add function we just covered. Here, the interesting thing here is the variance. So in a dynamic language, it's quite common to have slightly different variants of the same operation, like adding 2 temporary values, adding 1 value and the constant, and things like those. Here, since Xu-Deegen understands the type system as we covered before, we can specify that the constant is statically known to be a T-double not none, and the Xu-Deegen can do optimizations accordingly. For example, if T-double LHS is known to be a T-double not none, then since T-double not none is the subtype of T-double, we can know that LHS dot is T-double is always true. So the check here can be elided. So, and there are also more complex optimizations that we support, but due to time constraints, I'm unable to cover it right now. And from this input semantic, Xu-Deegen automatically generates a bytecode builder API that allows the user to construct the stream of bytecodes from the input source program. Like this, it just creates an add saying that LHS is slot 1, and RHS is a constant double, and the output is in slot 2, things like those. And the Xu-Deegen automatically generates highly optimized implementation of the interpreter and the JIT from the semantics. And I don't have time to cover the exact generated assembly, but it's, yeah. Now let's take a look at the JIT tire. So as we explained, it's completely free for language implementer. And since everything is automatically generated from the input semantics. And it features extremely fast compilation speed and good execution code quality. And almost all the optimizations in JavaScript cores baseline JIT. So the JIT is automatically generated by a complicated, sophisticated pipeline at build time. So as we can see, we take in the execution semantic of the CBP code, and we compare it to LLVM-IR. And then we first need to lower the Xu-Deegen APIs, like the core and the return and throw arrows and things like those. And then the thing is that for JIT, it's important to burn in constants. So the thing is that at runtime, everything in the bytecode stream are constants. So the thing is that we automatically identify those constants and generate codes, JIT codes that have these constants hard-coded into the instruction stream. And this and a few more extra passes are needed to handle all sorts of quirks about the constants. And inline caching is another important optimization for the JIT. I guess I don't have enough time to cover all the details, but I'll cover a little bit of it. Then the LLVM-IR is compared to textual ASM. So the thing is that LLVM is not really designed for dynamic languages. So the thing is that we have to implement some of the optimizations unsupportable by LLVM by ourselves. And how we do it is that we compile it. We do some of the tricks at LLVM IR level, and then we compare things to a textual ASM, and then we transform the assembly to achieve some of the optimizations on doable LLVM, like inline caching and the hot code splitting. So the hot code splitting is that we try to split the code into a hot part and the cold part. So dynamic languages has a lot of slow paths, so it's important to like put those slow paths into a code parts so that the code locality is better. And then we compile this into an object file. And sorry, I just realized I didn't cover copy and patch. Okay, so the thing is that the generate compiler is not using LLVM at runtime. So how it generates code is by copy and patch. It's a trick invented by me a few years ago. So the idea is that you compile the code you try to generate into an object file, and then through some hacks, you can extract the object file into a stencil, so that at runtime, all you have to do is to copy the stencil and patch some of the simple values. And that's how we generate code at runtime. And then we have everything needed for the JIT compiler. And we actually generate the compiler implementation in LLVM IR and compare it to get the JIT. To get a slightly concrete view about the JIT. So the idea is that the JIT at runtime takes in the stream of bytecodes as input, and it generates the two pieces of JIT code, the hot logic and the cold logic. And it also statically generates the slow path. And at the time the JIT code executes, you start in the hot logic, and at the time something unexpected happens, like the add is not the operand of the add is not a double. Control is transferred to the JIT slow path, which will further transform control to the ahead of time generated slow path. And after the slow path is done, we transfer control back to the hot logic again. And that's basically how the JIT works. And now let's take a look at a concrete example of the add. So as you can see, the generated code has holes in it, like 1, 2, 3, 4. And every hole is defined by an expression. So at the time we JIT code, these expressions are executed, and the outcomes are like burnt into the instruction stream. For example, if we are executing an add of slot 1 and slot 2, then the whole 1 is going to have 8, and the whole 2 is 16, and the JP is jumping to the slow path, the address of the slow path, and the jump 6 is going to be the address of the AOT ahead of time generated slow path. As you can see, since everything known as runtime constants are just constants in the instruction stream, the code quality is good for baseline JIT. Yeah, so I guess I don't have time to cover inline caching. And inline caching is another important thing that Xu-Deegen supports. So if you are trying to implement inline caching by hand, it's really hard. It takes a lot of assembly knowledge and other things. But thanks to Xu-Deegen, we invented a clever framework to automatically implement inline caching from the execution semantic of the bytecodes. Yeah, so I guess I only have less than a minute left. So for conclusion thoughts, well, so of course Degen as a research project, it has its novelty, but I don't really think it's the top contribution. So let me ask another question. What's LLVM's top contribution to the world? In my opinion, LLVM's top contribution to the world is the engineering that's put together decades of the compiler research into an infrastructure for any static language. And in my opinion, that's also the story that I dream for Degen. So it's the engineering that puts together the expensive lessons of JavaScript core, V8, and the state-of-art engines like this into a reusable infrastructure for dynamic languages. Yeah, that's, of course, it's very hard, and currently it's still quite far away, but we are at a good start. Yeah, that's it.
Questions?
So any questions? I guess I should not disconnect right now. Any questions?
Yeah, hi, thank you for the presentation. So you have your reasons for picking Lua. I didn't quite catch them, although I've been exposed to your work before. Are there any blockers for Python playing the same set of tricks?
Yeah, the thing is that Degen is designed to be a generic compiler generator, but Python is a really complex language. It has a lot, the semantic of Python is huge. It's a lot harder than Lua. And also Python has all sorts of exotic features. I mean, if you are just a conventional Python user, you probably wouldn't heard of this at all. But as a language implementer, we have to deal with all of these corner cases. So targeting Degen for Python is going to be a lot harder than for Lua. But I mean, conceptually it's doable, but in practice, it's all about engineering. And Python takes a huge amount of engineering.
So I'm curious, what's the hardest fruit to pick, or top of the list is most complicated semantic to handle?
For Python?
Yes.
I guess probably it's, I mean, I haven't investigated it deeply, but I think probably it's the class inheritance semantics, because for Lua, if you do an add, then if both are doubles, then it's always a double. But in Python, I think you can somehow inherit a subclass of double, of integers, and that's going to change semantics, and it's probably, yeah.
Thank you.
Hi, thanks for the talk. And I mostly just have some technical questions that I have on some of the slides. What does the library do as opposed to the LLVM parts? Does the library merely provide wrappers that you will transform them into code generators in a later stage? How does that work?
Sorry, I didn't get your question.
I think in one of the slides you showed us that Degen has a library part, and I think in the grid.
Which slide?
The one below it, number 16.
Number 16. Yeah.
Yeah. So so there is this Degen API. Oh, I guess this API is provided for the LLVM code base, I guess.
So the Degen API is just special things needed for the execution semantic of the dynamic language. For example, this throw arrow and
these are user space programs from LLVM's point of view, right?
These are just placeholder functions from LLVM point of view.
Oh, okay.
And we will
Gotcha.
lower them to the concrete implementation for the interpreter and the JIT. For example, in the interpreter, if you try to transfer control to the next bytecode, the thing you do is that you have to check the dispatch table and get the implementation function of the next bytecode and jump there, right? But for the JIT, if you are trying to transfer control to the next bytecode, it's a jump at the instruction level, right? So the implementation is different. So the thing is that by providing Degen APIs to abstract the semantic we need, at build time, we can actually lower them to different implementations we need.
I think I still have some questions. Maybe we can take this offline.
Yeah, sure.
Thank you.
Thank you for the talk. I also have some technical questions. Maybe I didn't understand everything correctly. There is a slide where you say that there is an AOT slow path that is generated at build time. I'm wondering how you can do that for a, let's say, a Lua program that's only going to be read by the generated compiler.
Oh, so the AOT slow path is like all sorts of weird semantics in Lua that users would not use normally. But the thing is that as a language implementer, we have to support it anyway. So the thing is that, for example, if you take a look at this add, if t double, if you are adding two values that are not double, then you have to throw out an arrow. It's not expected to be done commonly by common Lua programs, right? So the thing is that if you generate JIT code for all of this, the generated code is going to be huge. And we don't want to generate huge code since it takes time and memory to generate code.
Oh, okay,
so the thing is that we put some of this slow path as AOT generated code and only cool them.
So can I think of this as, can I think of the AOT slow path as part of the Lua runtime library then? You know, part of the standard exception handling code path perhaps? Because if it's part of the user program, I still don't know how you can generate slow path at degen build time.
We know, okay, so we know which code are slow paths. So we have a few ways to specify slow paths. One way is by type. So if we know that an add is almost always going to have two doubles as type, then we can actually analyze this function and split out this part into a separate function, and that's a slow path. And another way is to say that some code is slow path by hand. So we can simply has another slow path logic, and inside the hot path, you can jump to the slow path, and that's how we know if something should be in the slow path or it should be hot path. Yeah.
Okay, I have one last question.
May I suggest we take the rest of the questions offline? We're already 3 minutes over time.
Sure.
Thanks, everyone.
Thank you.
We'll take a short 2 to 3 minutes break, and a couple of audiences who had questions, please take those with Howren offline. And let's thank the speaker once more. Thank you.